Cornelia co-directs a perception and robotics group at the University of Maryland, where she works with her senior postdoc and very experienced researcher, Levi.
Levi. Also,
okay, just like Levi's, yeah.
I'm still a graduate student, by the way. I'm not a postdoc.
Oh, you are? Okay, well,
yeah.
You have the experience of a postdoc. And anyway, Cornelia's research is in the area of computer vision, robotics, and human vision, focusing on biological inspired solutions for active vision systems. And her publications span a very broad range, actually, from computer vision to human audition to spiking neural networks and embedded vision systems. And she got her master's and PhD in Austria. And she's been the PI and one of the chief organizers of our National Science Foundation sponsored Telluride Neuromorphic Engineering and Cognition Workshop for the last 7 years or so, I guess, Cornelia. And she was formerly on the technical program committee of CVPR, and she's well known in the whole computer vision community. And today, she and Levi we'll talk about a great event camera and IMU and LiDAR data set called EVIMO2, and what they did with it to solve the very difficult problem of segmenting moving objects from a moving background and a moving camera. I have enjoyed working with you, Cornelia, very much over the past decade, and always enjoying seeing you and your great family every year in Telluride. And thank you both for coming today.
Thank you. All right, so this is what you see on the EVIMO dataset, and it was created by Anton, who is not here, who studied it, Levi, and myself. And our motivation was to study the problem of segmentation, because we really feel that's where there is an advantage of the event camera that doesn't suffer from the blur like we have in video and gives us this good boundary information. But there were no real data sets there to evaluate object motion segmentation very accurately in this general problem of structure for motion. So we went on to first create this first data, originally a first data set that is multimodal, because we used our Vicon data set to get ground truth. And in the original version, we scanned the room at lower resolution with a standard camera. We only had one DVS camera in the original version, the Davis 340. And we high resolution scanned a few small objects. And you will hear how we combined them then in order to create accurate 3D motion of both the background and the object, as well as accurate localization of the objects. Then we understood the need for learning and went on to create a much larger data set with more objects and more cameras, the EVIMO2 that Levi Berner has been in charge and will tell you about now. And I will finish then with two applications where we really use the data set for learning that also created the necessity for this project.
All right, thank you for the introduction. So I'm going to go through the EVIMO2 dataset and its main features, including the recorded quantities, and then I'm going to explain how some non-traditional quantities are produced from that are useful for the object segmentation and motion segmentation. And I'm also going to, right before Cornelia takes back over, I'm going to talk a little bit about what our next plans are for the next version of EVIMO. So EVIMO2 is very much like EVIMO1, but it's more cameras with more objects and longer recordings. This on the left, can you see my cursor, by the way?
Yes, we see it great.
Good. Okay, so this camera on the left, this is the recording rig that we use. It has 3 event cameras, one on the left, one on the right, one in the middle, and one RGB camera right here. This camera right here is actually not used, but it's another event camera. So there's 3 simultaneous event cameras running and 1 color camera. We use this camera inside of a Vicon motion capture room that's pictured in the middle. This system has many Vicon motion capture cameras around the edge that allow tracking the position and the orientation of a set of objects within the scene. On the right, I show one of our objects that we use. So we have a collection of maybe 20 or so objects that are scanned in high resolution to get the 3D models. And these objects have Vicon motion capture markers on them so that they can be tracked by the Vicon system. So the camera is tracked and the objects are tracked all within this room. Now, by doing so, we have enough information to solve what's called the rendering problem, the same process that's done in video games or rasterization. And that results in the scene I have in front of you. So I'll walk you through it. So there's 4 cameras being displayed here. The RGB is on the top left, and then the 3 event camera results are shown in the other quarters of the screen. On top of the RGB and the event data is overlaid a segmentation mask where a color corresponds to an integer ID that corresponds to an object's identity. So as you can see, these masks are per pixel and very detailed. We also, in the process of generating the segmentation mask, end up through rasterization, we end up with a depth map shown by the black and white graphs along this video. The white is farther away, black is closer. And again, this is very high resolution.
Okay, why, one thing's confusing, why is the bottom view rotated 90 degrees?
It's because the cameras are rotated 90 degrees on the rig. And so that's the best way to make a video. Yep.
Oh, I see. Okay.
Yeah, see how these are actually 180 degrees? Yeah.
Okay, thank you.
I do get that question a lot. Yeah, so that's what it produces at its base level. It produces these raw camera recordings, these depths in each of the camera frames, and the segmentation mask overlaid. And with that, we can do a lot of interesting things. Just before I get into those interesting things, I want to point out something else that we have, a piece of software. While we have easily viewed videos on the website that allow you to look at every sequence, we also have a viewer that allows you to inspect every sequence at millisecond precision. And this is really great for seeing when you're doing especially classical algorithms, if you have some part of your algorithm that's not really working right and you want to understand why, this tool can probably help you. It will show you all the data from all the 4 cameras, all their different views, and so on. Okay, now before I go into what we can generate with this, I do want to define or just carefully explain what we actually have. So what I showed you before is the object poses. This is a transform from the object to the Vicon frame. And we have the camera poses, which is a transform from the camera frame to the Vicon frame. We also have the events. We have the classical images. We have the per pixel depth for those images. We also have per pixel depth for the event cameras at chosen times at 60 FPS. We also have per pixel segmentation for all of those frames. Of course, we also have the intrinsics and extrinsics of the camera lens parameters and their relation to the various Vicon transforms. We also have IMU data from 2 of the cameras. So the first thing we can generate with all that data is optical flow. So we use the depth in the event camera frame or the color camera's frame. And basically all you do is you take the depth that's in one frame and you use the transforms I described earlier to rotate all those points, back project all those points in the 3D world, and then rotate them into the new camera frame. This has to be done on a per object basis because each object actually moves differently than the background. So we can see here the cars going down and moving. Now, I do want to point out the colors flicker a little bit, and that's just because it's not because of noise, it's because the color plot is normalized. The magnitude of the flow shown is normalized, so we get as much color per frame as possible. And to show you, this is one of my favorite shots where I found while inspecting the generated flow. Because we used high quality 3D scans of the models, we actually get almost, I've never seen optical flow plots that look like this. So on the right, we have a toy car that's tumbling over end from right to left. And you can see the port in the flow field, the parts of the car that are actually stationary with respect to the camera and the parts that are actually moving and which way they're moving in great detail. So really from this, we can see the car is not just moving one way at one speed. It has all these different speeds due to all its different crevasses and parts on it.
Yeah, that's cool.
Thanks. Okay, so now we get into stuff that's a little non-traditional. So we have optical flow, that's great. But something we don't have is we don't have ground truth spatial gradients, which can be important for event cameras in the event camera frame at a per pixel level. We also don't have per pixel brightness. And while this isn't necessarily useful to have for deployed algorithms, it is sometimes useful for training algorithms if you want to generate certain types of ground truth. Based on all the measured quantities that we actually have enough information to take RGB data from the RGB camera taken at a different time, at a different place, with objects at a different position, and reproject those pixels, those color pixels, back into their location on the event camera frame. So what I'm showing you here is an event count image exactly as captured by the DVS camera, with those RGB samples from a color camera resampled back into the frame. And you can see the checkerboard is most obvious. You can see that this is very well aligned in a way that couldn't be done with an approximation. And it works for the moving object as well. There are some parts here. You can see that there's not color everywhere on the event camera frames. And that's because if the RGB camera and the event camera frames don't overlap, we can't reproject the RGB data. There's none, we don't have any, we don't know what it is. That can also happen on the car. If you watch carefully as the car moves down, you'll see a black flickering in front of the car. And that's due to occlusions where, because the RGB frame and the event camera frame are at different times, they weren't able to see the same regions of the objects. And so we get some occlusions. Even if they were perfectly synchronized, there would be still some of those occlusion parts, but they would be much more minor. Okay, and so because we have, and this is an example of what we can do with this.
Can I ask a quick question? I'm sorry.
Yeah.
So that looks very clever, but I'm wondering from a machine perception point of view, what is the advantage? So you have objects that you already know what they are, right? Mm-hmm. And then you're just putting this color information back on essentially synthetically. Yep. So I'm wondering what the advantage is from a machine perception point of view, what that's actually buying you.
This provides you ground truth that you can use to compare the results of your perception algorithms to. So for instance, there's been a lot of work of events to images. This provides you ground truth of events to images with a real camera with moving objects in indoor scenes. You would not feed this data into the algorithm as an input, but you might use it to evaluate its output.
Wouldn't you have lighting issues though for that? I mean, wouldn't the color that you're seeing and the color that you would perceive in the real situation be very different? So might it not be confusing from that point of view?
So you might, so first of all, if most of the event to images are to produce a grayscale image. So if you were to produce a grayscale image and you wanted to compare it to this image, you might compare it to a loss that automatically adjusts for an unknown contrast or an unknown bias or a logarithmic scale.
Okay, sorry to interrupt.
No problem. Okay, so another one of the ground truth quantities we can generate with this is actually normal flow. So we can actually get high quality normal flow in the frame of the event camera. Now, for those who aren't familiar with normal flow, it's a combination of optical flow and spatial gradients, image intensity gradients. And basically, it's a vector that points in the direction of an edge in the brightness image, but its length is determined by the size of the magnitude flowed. So by the equation down here, we have on the right a vector, which is direction from the spatial image gradient. And the left, we have a magnitude, which is due to the optical flow dotted with the gradient. You can estimate normal flow without optical flow, and that's why we're interested in this, but we need ground truth to compare our results to. And by doing all these steps that I showed, the optical flow, the reprojected RGB, we're actually able to get very high quality normal flow at a pixel level in the event camera frame.
Yeah, useful.
So I want to point a couple of statistics. I'm just going to point to the big ones here. So the data set is 41 minutes long, 21 minutes of test, 20 minutes of train. We have several categories of sequences. So we have 3 minutes total of independent motion. So these are objects falling down boards, being thrown in the air, that kind of thing. We also have about a half a minute of very low light sequences that we were experimenting with. In these sequences, the event count images are very blurry, for lack of a better word, due to the low amount of events. We also have structure for motion sequences, 18 minutes of that. In these scenes, the objects don't move, just the camera moves. This is thought to be very helpful with pre-training for motion segmentation algorithms. We also have low light for that. And then finally, we have a large test set of rudimentary motions. These are like over a board, moving left, right, up, down, or basic rotations. And the idea is that if your algorithm works on the upper parts, it should work on the basic sanity check motions as well, as would be typical of somebody just trying something when they downloaded your code. And there's a lot of sequences. There's like 170 total. Now I want to talk a little bit about EVIMO3 and what our goals for it. I can give you a quick teaser. The main advantages are technically we're going to simplify the generation pipeline and allow much better data generation that we can run while we're recording. And because of that, we will be able to review our data live during a recording day and re-record scenes as appropriate to get better shots, better camera angles with richer motions. In particular, we'll be able to handle situations where maybe the Vicon is losing track of an object. And we won't have to be very conservative about making sure it doesn't, because we can just review a sequence and re-record if there's an error. And this is made possible by this viewer I show here. So this is from one of our previous sequences, and I'm actually moving a virtual camera here that's using all the object models and all the camera pose to rerun the recording live. And I can see things from different angles and figure out where I might want to place the camera in the next shot. With that in mind, let's see, next slide, there we go. We also want to get more natural sources of independent motion from sources that you might see in everyday life. So we're looking to use techniques we've learned from recording violin data sets in another project. By the way, the second version is coming soon. And we will hopefully have humans in these scenes, maybe throwing objects between each other, interacting with objects, that sort of thing. And we hope to have those same per pixel segmentation and depth maps available for the humans, though of course it may have to be slightly approximated since we cannot 3D scan a flexible human body very well.
Okay.
All right, and I think with that, I'm going to pass to Cornelia.
A few minutes. Originally, we started this for motion segmentation, and we did work on both learning and non-learning based approaches. And it's really good for learning. Yes, please, the obvious thing. So I will talk about quickly 2 papers. One paper that follows this concept of the self-supervised learning, that, by the way, the neuroscientists I've seen picking up on that too, confirming that this prediction is closer to the motion pathway. The general concept is that we can learn from small time slices, in our case, a depth network, at depths, and from multiple images in general, which in our case, we used different amount of time intervals to align. So the events over different amounts of time intervals. We can get, if we have these 2 sources of information, we can estimate from that the optic flow, and on the basis of that, do the alignment. That's the self-supervision. However, we can also now learn independently moving objects. And that was the idea why we needed a data set. And the way we did it, there's a lightweight architecture under the hood. Okay. And what we do is we write our function for optic flow or 3D motion that needs to be aligned as the camera motion, P ego, which you see in the formula. plus, yes, the sum of the residual motions, which come from the independently moving objects. And they are described by the motion mask, and we only have the translation here because you can't really differentiate on a small object for all components. Now, the network here in a supervised way, using our data set with masks, learns in an encoder-decoder architecture the motion at the encoding part, and then at the decoding part, it's
Cornelia, could you point to these parts? I don't know what you're talking about in this
yes,
picture.
because Levi, please point at the
Yeah.
arrows, at the M and the T. Yeah. Mm-hmm.
M and T are here.
Yeah, so this is the M, that is, so we model the motion as this linear combination of background, as a camera plus foreground moving objects, where the T is the residual translation in the formula of each individual object, and the M is the motion mask. So how likely is the pixel to correspond to a particular mask? And you use an encoder-decoder architecture where the encoding level, the T's are learned, and then at the decoder level, the likelihood of this motion mask probability is learned. And you formulate it as a combination. And the next slide now shows the result. Here are some results. With, as you see, the DVS input labeled the depths, the estimated depths. And you see it learns very well ground truth, estimated pose, and the estimated mask. And while this was done with a small data set, at that time only 3 objects, it does some generalization, but of course not everything. But the novelty is that this was the first work ever to actually estimate 3D motion, accurate 3D motion. And also, as mentioned, the warping of individual slices is really done on the slices itself. And then we moved on. We always were of this idea that you need to, there is additional information in the point clouds available. And that is in the next slide. What about if we use the cloud, and this is ongoing work too, we really want to take advantage of the whole clouds over longer, because they do carry information for those situations that are very difficult for computer vision. So here's 3 examples on the left, the C translate motion along the Z-axis with the time encoded as color. So from red to blue, XY translation, so parallel to the image plane, or a rotation around the Z-axis on the right. And what your representation is on these point clouds, if you have them available, the optic flow basically lies in the tangent plane to those clouds. That's the idea. So what you can compute is then the normal perpendicular to these tangent planes. And that's also what we feed into our network. What we have been stressing, the normal is really something that's equivalent to biology. It is the output of filters, simple filters. That's the motion representation. So showing the next slide, we can, as you see on the right, if we look at, the difficult cases are when objects come together in the scene, when you have one object overlapping another one. And that can be really only distinguished from if at the point you have 2 optic flow values. So if you start fitting the normal flow to optic flow in a neighborhood, which means you solve some equation least square estimation, you recognize this. Can you point to the green contour? And then at the bottom, the contour, you recognize this when 2 things come together, one overlaps the other on the basis of two different flow values. And that is available through in the information in the point cloud. That's still algorithms need to be developed. What we did in our work was the first work to take advantage, and we used a graph convolutional network. Details lie that we had 5 layers. Each of them at the nodes, we get 64-dimensional vectors. These 5 layers sequentially reduce the resolution, and we feed into these layers the graph, local graph of events. So what you have in the neighborhood is then just take X, Y, T as the cloud, and you connect them by similarity. But since we are really looking at the surfaces, we also filtered them so that we are going basically perpendicular, parallel to the surface and in a certain range, and do not consider the whole range.
Okay, Cornelia, I'm sorry, buddy, we're kind of over timed. So
Okay,
let's...
so basically we are done. Just show the next one shows results. Which you see when you get more and more, if you consider longer time slices, you get better and better results. There is an advantage, and of this demonstrating the usefulness of using longer clouds in the learning. So thank you.
Thank you very much. That's a really cool data set. I'm sure a lot of people will find it very useful and look forward to the next one. And is there any questions from the audience?